Uh, everyone can hear me, right?
Yes.
Yes, good morning,
Yes.
doctor, and can hear you.
Okay, thank you very much. So let's start our class. Just 2 minutes to go through our Blackboard. So I have just revised the grading policy, and I have mentioned those revisions in the yellow highlighted color. Okay, so just take a note of that. So, I have changed this to class interactions to class questions, and there was a typo here. I fixed that typo. And this two things I told verbally in the first class, but I have written here. So the first thing is about the class questions. It will be through Zoom polls or in the form of oral questions where the students need to answer in the private chat window. And the second thing is the classwork at the end of the semester, it will be normalized to 75%. Okay. And besides that, if you see, there is another important message, and please go through this message. This was also posted, I think, in the first week. So just go through all of them. And if you have anything, let me know. So let's start the class. In the last class, we yes.
What did you decide about the last questions?
Let me think about it. I will not decide so early. Let me think about it. There were two questions, right? So let me think about it, and then I will get back to you. No need to worry. Okay, because we are going to have 2 to 3 questions every week. Maybe after 3-4 weeks, I will let you know. Okay, so let's start. Just a second, let me open the sticky notes. Okay, so in the last class, we looked at the line charge and also the surface charge. So surface charge in the form of a infinite sheet, we tried to get its expression for this infinite sheet using the general expression of Coulomb's law. And in the end, we found that it will be rho s over 2 epsilon. Okay, so for a point charge, so we saw that electric field is proportional to 1 over d square. And for the line charge, we saw that electric field is proportional to 1 over d, which is nothing but d is nothing but the distance between your source and your observation point. And now for the surface charge or the sheet, we found that your E bar is independent of the distance t. So these are the 3 important observations that we found till now. Okay, so if you go here, this is the electric field that we got. So the electric field is equal to rho s over 2 epsilon, and now it is AZ because this is our z axis. And how does it looks like? These are the electric field lines, or the electric field vectors. Sorry, electric field vectors. So rho s over 2 epsilon. So if your point is close to your sheet, and if your point is far away from the sheet, it doesn't matter. It will be the same value, rho s over 2 epsilon. Okay, I think this is where we stopped in the last class, and this is for the general expression. Now, we have a small example here, and the example is for the parallel plate capacitor. So what it is saying that we need to find the electric field due to a parallel plate capacitor. And the parallel plate capacitor, they have charges of rho s and plus rho s and minus rho s on the 2 plates respectively. And this is our drawing. So you have an upper plate, and this upper plate has a charge of rho s. Let me reduce this. So the upper plate has a charge of minus rho s and the lower plate has a charge of plus rho s. And these two plates are in the xy plane. And that's why this is your z axis. And that's why I have written here with an arrow AZ. That means this is the z axis. If this is the z axis, then your AZ, the unit vector, will be along the z axis. So this will be your xy plane. So your both plates are in the xy plane, and we are assuming that both the plates are infinite. So if both the plates are infinite, then what we are doing is we are not trying to find the electric field which will be inside these two plates and the electric field which will be outside these two plates. So the inside is this one, E inside, outside is E outside, and the material between these two plates is epsilon. And the material outside is also epsilon. Okay. Now, how I am going to do here? See, now E inside. So we are now finding inside. So let's do it here. So if this is your plate or this is your sheet and it has minus rho s, okay, then how would be the direction of the electric field for this minus rho s? As we have seen that for a sheet with a charge of rho s, positive charge, so the electric field is always going away from the sheet. See, very similar to the point charge, going away from the sheet. So if the charge is negative, then the electric field will be coming towards the sheet. So here also, it's the same thing. So here, this is my negative charge. So this negative charge, the electric field that it will generate will be coming towards it like this. Like this, towards it. Towards it. Now, and its value is what? Its value is rho s over 2 epsilon. Okay, maybe for the values, we will look at it later. Okay, now the lower sheet. Okay, so the lower sheet. So let us first look both of them separately. So this is my lower sheet. Oh, sorry, this should not be an arrow. So this is my lower sheet and it has a charge of plus rho s. So what will be the electric field of this one? It will be going away. So it will be like this. Clear? So it will be going away. Now, let us join these two because the total electric field, so my lower sheet is here, plus rho s. So what will be the electric field which will be generated by the roll field? Let's draw on the same figure. So it will be going away. So it will be going away. See, it will be going away. And here also it will be going away. All right. And here it will be going away. Clear? Now, what is happening? Let us find the total field now, because this is E bar inside and this is E bar outside. And this is also E bar outside. So what do you see? You see that the electric field outside, they cancel each other because one and the other are in opposite direction. Here also, they cancel each other. They are in the opposite direction. Only the electric field which is between the two plates, they are in the same direction and they are pointing from your positive charge sheet to the negative charge sheet, which is what we have seen in the point charge. The electric field originates from a positive point charge and terminates at the negative point charge. So therefore, from positive to negative. And this is our electric field, which is nothing but the addition of the electric field generated by the upper sheet and the lower sheet. So that's why if you see here, E inside is E upper plus E lower, which is plus rho s over 2 epsilon Az plus rho s over 2 epsilon Az is equal to rho s over epsilon Az. Whereas outside, they will be opposite. So they will cancel each other. So you will get 0. So your E inside is nothing but rho s over epsilon times Az. This is your answer for the parallel plate capacitor. Okay, but just there is a one very important note which I am writing it here, because many times what happens is the student gets confused, whether what should be the sign, so what they end up is they end up using the sign for the charge and also putting the sign for the unit vector. So eventually what is happening is these two signs may cancel each other. So that's why I always suggest my students that let the unit vector decide the sign. So in this case, if you have a negative charge sheet, so which is this case, a negative charge sheet minus rho s, and if this is our if this is our electric field, so this is our electric field, then how do you write the electric field? How do you write the expression? So E bar is equal to rho s minus rho s over 2 epsilon, and this is my Az, right? So minus rho s over 2 epsilon times, if you are seeing this side, because if I assume this is 0, then for z less than 0, so it is minus rho s over 2 epsilon times Az, correct? Because it is in the same direction. And E bar is equal to, for this side, minus rho s over 2 epsilon times minus Az. Z is greater than 0. So this is coming as rho s over 2 epsilon times Az for z greater than 0. Now, can you check, are these two correct? See the direction here. What is the direction here? It is going up, right? It is going up. It is along the z direction. So if you see here, what you are getting, let me go back. Okay, so if let us compare it with this one. Okay, I cannot do that. Let me move here. So if you see here, what is happening? So this is Az. So this is going in the z direction, Az, and this is my charge minus rho s. Now, these are the expressions that we are getting, correct? These are the expressions that we are getting. Now, if I apply here, then let's see what results we will get. So let me use the annotation. So let us see what results we will get. So down, down, down. Okay. So here, this is what? Rho S over, minus rho S over 2 epsilon times AZ. And this is rho S over 2 epsilon times AZ. And this is minus rho S over 2 epsilon times AZ. These are the field values for this negative charge. Now for the positive charge, for this charge, so it is going away. So this will be the field, purple. For this charge, for this line. Now what this will be?
Rho S over 2 epsilon.
So this one will be rho S over 2 epsilon AZ, rho S over 2 epsilon AZ, and this is minus rho S over 2 epsilon times AZ. Correct? So this, oh, sorry. Let me just erase this. So this is rho S over 2 epsilon times AZ. Now, if you see this, what is happening? You are seeing that the term which is inside, although the vectors should add, but if you see the expressions, they are getting subtracted, right? And here, when you look at the vector arrows, they should cancel, but the field, they are getting added. This is because for the negative charge, for this negative charge, you have to put minus, you have to consider minus only at one location. And guys, this is in general throughout this course, for especially when you are dealing with negative charges, you have to consider negative only at one location. Consider negative either in the charge or let the unit vector decide it. So when you want the unit vector to decide it, then just work with the magnitude of the charge, which is rho S. Okay. So again, I'm repeating, for any negative charges, if you are dealing with any negative charge, especially with this kind of sheets, okay, infinite sheets, and whenever you have a positive charge and the negative charge adding things, then it's, and whenever you are seeing something which is going wrong, that means, see here, when I draw, I'm getting different, but when I'm writing the expressions, I'm getting different. So please think. And then the best solution to this, I would suggest, is use the magnitude of the charge instead of positive charge and negative charge. And just a second. Oh, it is not moving. So let me move this. Yes. So use the magnitude of the charge instead of the positive or negative charge, and the sign will automatically be taken care by the unit vector. It will be taken care by the unit vector once we know our electrostatic field direction. So it's better if we always follow this suggestion. So in this case, now let us correct this. So what is the correction here? See, if this is my AZ direction, then this. Let's work with the magnitude. So magnitude times 2E, and this is the same direction as AZ. Yes, so this is okay. Now here, same direction as AZ. Yes, okay. Here I'm working with the magnitude. So let me rewrite this. So in a proper manner. So here what I can do is I can write, I will use the magnitude rho s over 2 epsilon, and now it is minus AC. So this is giving you minus rho s over 2 epsilon times AC. And now let's come here, this red one. So now let's correct this. So now look at this one. So what it should be, I am working with magnitudes. So let me erase this and let us work with magnitude. So what will be the magnitude? So magnitude, so I will not consider this minus rho s, I will just consider the magnitude rho s over 2 epsilon, and then I will look at the unit vector and let the unit vector decide the sign, because it will automatically taken by care by the unit vector sign. So unit vector signature is what sign is what? Positive. So it is AC. So it is rho s over 2 epsilon times AC. Now here, what it will be? The arrows are going down. So the unit vector will be minus AC. So the unit vector will be minus AC. And here also, let the unit vector decide, not your charge. So here it will be rho s over 2 epsilon times minus AC, and here also rho s over 2 epsilon times minus AC. So in this case, now what you will see, that everything is consistent. So this will be added and they will be subtracted. Okay, so this is an important note that you need to take care of. Okay.
Doctor,
Yes.
is it valid for the whole course or only for this type of questions?
As far as I know, it should work for any negative charge, but I will confirm this with you. But what I can say is, for this sheet of charges, this is always valid for the sheet of charges. And I will check. I'm quite certain that this should be, applicable for any negative charge throughout the course, because from my experience, if you always work with unit vectors, then the unit vectors will automatically take care of the sign of the negative charge. Okay, so I will confirm and let you know in, say, next class or by next week. Okay, so this is your sheet of charge. Now you have the last example, and the last example is, so we did for a line charge and we took an example, we did for a sheet of charge, we took an example, and now this is an example of a volume. So it is saying that develop an expression for a sphere of radius A. So you have a sphere of radius A. So here you have a sphere of radius A, and which is centered at origin, and the volume of this, and it has a volume charge density rho v, and it is uniformly distributed in the sphere, and my observation point is 0, 0, z. So you have now a sphere. You have a sphere origin. So this is okay. So let me use this as X, this as Y, and this as Z. And now my observation point is here, which is 0, 0, Z. And we need to find, and it's a sphere. Sphere, it's a solid material. Okay, so it's a completely solid material, and it is filled with a volume charge density rho v. Okay, so we are not going to solve in our class now. So this is our problem statement. And since we did it for the line charge and for the surface charge, for the volume charge, I'm leaving it to you. So this is in the textbook. So you can go and look at it in the textbook. So as I told you, for the line charge, for the surface, so see here, this is for the volume charge. Okay, so this is the volume charge. So you can go through the textbook, because again in the textbook, we use the general formula for finding the electric field, that is the general formula of our Coulomb's law. And then we solve it in a very similar manner as we did it for the line charge and for the surface charge. And we will see that the electric field is nothing but Q over 4 pi epsilon Z square AC, or E is equal to Q over 4 pi epsilon R square AR. This is the general expression. Okay, so you can go through this example at your home. So this is the expression that you will get, which is Q over 4 pi epsilon R square AR. Now, does this remind you of something? Does this expression remind you of something?
This is the field equation.
Yeah, this is the electric field for also, yes, Q over 4 pi epsilon R square AR. This is the electric field for also, yes, we don't have it on in this lecture.
Point
charge.
Exactly, yes. So this is also the same as the electric field for the point charge. So it's for point charge, or you know, your sphere of charge Q, or your point charge of charge Q. The expression is the same. And this comes from what is called as Gauss law. So Gauss law actually tells that this will happen. Okay, and that's why you see both these expressions, both the expressions that you get for a point charge and a sphere as the same, because it depends on the total charge, which is Q. Okay, so when we look at the Gauss law, then we will again derive the expression. We will again derive the expression, and there we will see this. Okay, so this I'm leaving it to you. So do it by yourself. And if you want, you can go through these pages of 122 and 123 and see how it is derived. And what we are doing here, just, you know, we are just, changing this by using the volume of a sphere, because the total charge is the integral over the volume times dV, right? So the total charge Q, you can find it in terms of rho v. So I'm trying to find Q in terms of the rho v, volume charge density. And we know Q is what? Integral over the volume charge density times dV, right? So this is equal to, I'm taking the volume charge density outside the integral times dV. So when I can take the volume charge density outside the integral, in our line charge, in our surface charge, you know, all these derivations, we always take our charge density outside the integration without any hesitation. Reason?
Uniformly distributed.
Exactly. That's why Uniformly distribution is very important, this word. And that is why in the example questions I have mentioned, it is uniformly distributed. Uniformly, that means it's a constant. And therefore, this constant can be taken easily outside. But if your charge is not uniform, then you cannot take it outside the integral. You have to keep it inside the integral and do the integration. Okay? And what is the volume of your sphere? You know, integral over the volume dV. What is the volume of your sphere? It is 4 by 3. Yes, pi. Yes, 4 by 3 pi r cube, right? 4 by 3 pi r. R is whatever radius. So 4 by 3 pi a cube. So this is rho v times 4 by 3 pi a cube. So this is my charge, which I can substitute here. And when I substitute here, I will get this. Rho v a cube over 3r square ar. So this is the electric field for a sphere of radius a centered at origin, carrying a uniform volume charge density rho v. Okay. So now let's go to our next part of our chapter number 4. And this is, so we did this lecture. So let's go to chapter number, the next lecture. And this is our next lecture.
Doctor,
Yes.
but the density is not uniform. I mean,
Yes, if the density is not uniform, then what are you going to do? If the density is uniform, what are you going to do? You have to keep your charge density inside the integration, because now the charge density will become the function of your spatial coordinates. So it will be no longer a constant. It will be a function of your spatial coordinates. And if you are in Cartesian or if you are in cylindrical, it will become a function of a spatial coordinate. So your rho v must be inside the integration when you do the integration. That one example is there in the textbook. You can look at that example. Let me just show it to you.
okay, doctor, if it's
This one.
coordinate, how
This,
can I
sorry?
evaluate that? If it is in terms of coordinate, I mean x, y, and z, how can
Yes.
I evaluate the integral due to the dv here in terms of variable v?
Yeah.
There is
So,
or just change dx, dxy, dz.
yeah, you have to do that. You have to do that. See, there is an example here. See, this is called as a non-uniform charge density. See?
Okay, clear, doctor.
So this is a non-uniform charge density rho v because it's not a constant. See, it depends on the spatial coordinate r. So when you evaluate this rho v dv, see, when you put this here, then your rho v cannot come outside the integration. So you have to substitute rho v with this expression and keep it inside and then do the integration. And as you mentioned, dv will be composed of, because this is spherical coordinates, the dv will be composed of d phi, d theta, dr, and then accordingly you have to do the integration. Okay?
Okay, clear, doctor.
Clear? Okay.
Yes.
Now let's go to the chapter 4. Now in chapter 4, we are defining a term which is called as electric field. We have defining a term. So we have first defined a term electric field intensity, right? E bar is our electric field intensity, which is volts per meter. Now here we are defining another term which is called as D bar. And we are saying that D bar is nothing but it just considers the material. So epsilon is the material in which your electric field is there. So if you are looking at an electric field inside, say wood, sorry, it's a dielectric. So inside any gas, then the electric field multiplied by the permittivity of that gas will give me a new vector called as D, and this is called as electric flux. It is called as electric flux density. Okay, so electric flux density. This is electric field intensity or electric field. This is electric flux density, and its units is coulombs per meter square. Okay, so this is the definition of electric flux density, and the main reason why people came up with electric flux density, because in some of the analysis it becomes easier to say do some derivations or do some calculations using D, because in D epsilon is automatically absorbed. That's why. So we should not get confused about this. So the only difference between these two is the epsilon. Okay, then the next definition is phi, which is called as flux. Okay, it's flux, and it's very common. It is used in mechanical engineering, it is used in electrical engineering also. This is in general flux with something which is coming. Now in our case, since we are applying it into electrostatic field, we say it as an electric flux. And the electric flux definition is nothing but it is the surface integral of d bar dot ds bar. That is, whatever is flowing through a surface, whatever is flowing through the cross sectional of a surface. Not cross section, sorry. What is flowing through a surface, just through a surface. So if you have a pipe, sorry. So if you have this as my surface S, and now this is my D here. So how much is the D which is coming out of this surface? How much is the D which is coming out of the surface is nothing but your electric flux, and which is equal to your surface integral of whatever D is coming out. And what is the formula to find the surface integral? It is d bar dot ds. And remember, the units of flux is again Coulomb, because D is Coulomb per meter square and the units of your surface is in meter square. So the answer will be in Coulomb. So this is called as flux. So we have now two new terms, electric flux, which is surface integral d bar dot ds bar, and the electric flux density, which is capital D bar, and it is nothing but it is epsilon times E bar. Okay, now we are going to the Gauss law. So this is the after Coulomb's law. Now we are looking at the second law, which is called as Gauss law. Now the Gauss law states that the electric flux through a closed surface is equal to the net charge enclosed. So the electric flux through a closed surface. So surfaces, there can be two types of surfaces. So this is, you might have seen this in chapter 3 and chapter 2. So first is an open surface. So this, let us assume this as an open surface. An example of an open surface is a plate. Okay, plate, or you can think it as a paper. It's an open surface. Got it? So this one. And what will be the unit normal of this open surface? The unit normal of this open surface, it can be coming out of our screen or it can go into the screen. Both are fine for a open surface. So if I show it in the 2D, if this is my open surface, if this is my open surface, then the unit normal to that surface, it can be this one or it can be this one. Both are correct. Both are correct. So that's why In an open surface, you can take any normal. Both will be fine. Now, second type of surface is called as a closed surface. So the closed surface, a good example of a closed surface that I can give it to you is your soccer ball. Your soccer ball is called as a closed surface. So inside it is empty, it is hollow. So it only has the outer surface, but that outer surface is closed. So the example is your soccer ball. That is called a closed surface. And for the closed surface, always the normal to that closed surface will always point outwards. Always outwards. No inwards. Here it can point outward because there is no we cannot define what is outward, what is inward in an open surface. But it can go here and here. But here, since it's a closed surface, it will always point outwards. Okay, so this is very important message. So for the closed surface, there cannot be any unit normal going inside. So if I try to draw this in 2 dimensions, so it will be like this. And the unit normal always will point out. You cannot have a unit normal inside. This is wrong. For the closed surface, it doesn't exist. So now what Gauss Law is saying, it's saying that if the total flux which is coming out of this surface, okay, so this is my closed surface, this is my closed surface, the total flux which is coming out of this closed surface is nothing but it is equal to the net charge enclosed. So there must be a charge inside that closed surface. So the flux which is coming out of the closed surface, the flux which is coming out of this closed surface must be equal to some charge is equal to the charge enclosed. The charge enclosed. And this is the reason for the point charge and the sphere to get the same expression, because it is according to the Gauss law, it's the charge Q. It's the charge Q which is giving you the electrostatic field expression. So the charge Q is carried by the sphere, no problem, but outside it will give you the same expression as a point charge carrying a charge Q. So if you see here, these are some of the examples. So suppose, so you have a closed charge here, S3, sorry, closed surface S3, closed surface S2, closed surface S1. Now this S1 is a closed surface which encloses 2 charges, Q2, Q3. Here it is Q1. Here it is nothing. So if I apply Gauss's law, what I will get to this S1? I will get that the closed surface integral d bar dot ds bar over my surface S1 is equal to the charge enclosed. How many charges are enclosed? Q1 plus Q2, superposition principle. And for S2, it will be Q1. And here, if there is nothing, then it will be equal to 0. So this is called as Gauss's law. So it's Gauss's law says that the flux going out of the closed surface, which is nothing but psi also, is equal to your charge enclosed. Now, we are just rewriting the Gauss law here. So how we are rewriting the Gauss law? We are just trying to say that, okay, if integral closed surface integral d bar dot ds bar is the charge enclosed, which is the Gauss law. Now, can I write charge Q as rho v dv for a very general case, right? For any general case, I can find the charge Q as integral over v rho v dv. Clear? Because your surface charge and your line charge, they are essentially special cases of your volume charge. So your volume charge is the more generalized one. So that's why I can say that this Q is nothing but integral over V rho V dV. Now I'm using what we have learned in chapter 3, the divergence theorem. So what does the divergence theorem says? It says that the closed surface integral of a vector field A over a closed surface is nothing but it is equal to the divergence of that vector A or the vector field A over that same volume which the closed surface is enclosing. Because, for example, if you have your soccer ball, yes, the soccer ball has a surface and the surface is closed. So when the surface is closed, inside hollow part, it is actually, your closed surface is enclosing some volume. And what is that volume? The hollow part inside is the volume. So this is what divergence theorem is relating, the surface integral with what is the volume which is enclosed by the surface integral. And it says that the closed surface integral of any vector field over this surface ds, closed surface ds, is nothing but the divergence of that vector field over the volume which is enclosed by that closed surface. So if I substitute this here, the closed surface integral d bar dot ds, can I write it as the surface integration? I am converting into volume integration, because the divergence theorem essentially allows us to convert a surface integral to a volume integral. So I'm converting this surface integration to the volume integration by finding the divergence of my electric flux density over dV is nothing but right hand side as it is. So now both of them are volume integrals. So therefore the inside terms must be the same. So therefore del dot d bar must be equal to rho v. And this is also Gauss' law. But since this is based on divergence, which is differentials, so that's why we say this del dot d bar as the differential form or the point form of Gauss law, and closed surface integral d bar or ds bar is equal to q as the integral form of the Gauss. Okay, now, so Gauss' law sometimes becomes very handy in finding the electric field due to some charges surface charge or the volume charge densities which are simple and which has some symmetries. Symmetries here I'm referring to that your electric field will be function of only r in spherical coordinates or only rho in cylindrical coordinates, or only x or only y or only z in rectangular coordinates. If you have these kind of charges who has these kind of electric fields, then it becomes much easier to find that electric field using Gauss's law. Okay, so that's why, so here we got the expression for a point charge using Coulomb's law, right? Now here, let's try to get the point charge using the Gauss's law. So what you need to do, that you first have a point charge Q1, which is placed at origin. Okay, then try to enclose this charge in a closed surface. And that closed surface is usually called as Gauss's surface. It's a hypothetical one. Okay, I think guys, it's time now. It will take some time for me to explain this. Maybe we will take it in the next class. Okay, so we will take it on Thursday. We will go through the Gauss's law on Thursday. So anything else you want to ask?